All right, let's finish up this chapter, shall we? Let us look at how we all will figure out whether our reaction mechanism was going to run Sn1 or Sn2 or E1 or E2. Looking at our reactants, how can we figure out what mechanism it'll go through, whether we're going to get substitution or elimination products? Note, this is not the easiest thing to figure out. There is a lot of controversy, especially if you have secondary substrates, because secondary substrates can do any mechanism. True story? Well, not true story. In fact, a long time ago, there was a big argument about mechanisms. Someone you may have heard of, a guy by the name of Julius Caesar. Yeah, Caesar was meeting with his friends in the Senate, and they were arguing about reaction mechanisms, as you tend to do. And there was a secondary alkyl halide, and Caesar was like, I think this is the E2 mechanism. And his friend Brutus was very adamant, no, this is going E1. And they were just arguing, and eventually Caesar got really ticked off and yelled, E2 Brute, and Brute was like, no, Brutus, no way, Caesar. And so Brutus stabbed him. I'm telling you, these arguments about mechanisms can get very heated at times, and may even change the course of history. So, that story is absolutely not true, but I like it anyway. I wish it were true. So let's look at our mechanisms now. We've made our graph here, our little chart of Sn1 versus Sn2. Let's go through all our conditions again. Leaving group. Sn1 wants a good leaving group. All these reactions need a good leaving group. If you have a poor leaving group, such as hydroxide, none of these reactions are going to occur. Substitution will not occur. Elimination will not occur. Sn1, good leaving group. Tertiary substrates to make that tertiary carbocation. They prefer weak bases or weak nucleophiles, such as water or alcohols, and protic solvents, such as water or alcohols. Sn2, substitution mechanism, good leaving group. Sn2 prefers primary alkyl halides, primary substrates, strong nucleophiles, strong guys such as hydroxide or alkoxide, sodium ethoxide. And they also prefer aprotic solvents. But recall from our conversation, the solvent is the least of our worries. You can get an Sn2 mechanism if you have a strong nucleophile in there, even if you have a protic solvent in there. All right, E1, as we said, is the same conditions as Sn1. Good leaving group, tertiary substrate, weak base, weak nucleophile, protic solvents. Yes, if you're running an Sn1 reaction, you'll get E1. If you're running an E1 reaction, you're going to get the substitution Sn1 products. E2 conditions, good leaving group, tertiary substrate, strong base. And recall, since nucleophilicity parallels basicity for the most part, strong bases are also strong nucleophiles, and aprotic solvents. So keep this in mind. If I were you, right now I would just copy this down, copy this chart down, and then as we go through some of these examples, you will know what to do, because you can look at this chart. Question: will you be allowed to bring in this chart for the exam? Answer is, of course not. You have to have this memorized. All right. So, there are a few things to note that kind of help us out. Good nucleophiles that are weak bases favor substitution. Remember, we had a couple of exceptions to our rules. We had some good nucleophiles that weren't really good bases. Prime examples of good nucleophiles that are weak bases and therefore will favor substitution. The main example, cyanide, Cn-. There's one that really only wants to do a substitution reaction. It's a really good nucleophile. It's not a very good base. And the others in there that we had, like SCH3 minus. Also, good nucleophile, not a good base. Those guys favor substitution reactions. All right. And our other exception, if we have bulky nucleophiles, or bulky nucleophilic bases, I don't know, they're not very nucleophilic, bulky bases favor elimination. A prime example is potassium tert-butoxide, OCCH3 minus. Tert-butoxide is a very large, bulky, sterically hindered base. It really doesn't like to attack carbons. It likes to attack the protons because the protons are on the outside of the molecule. Carbons are always buried inside the layer of protons, of hydrogens. All right. So let's take a look at a few right here at the bottom. If we react these two reagents, okay. First, let's look at our substrate. Note, do we have a good leaving group? Bromide, yes, good leaving group. So good, we can run our reactions. Is it primary, secondary, or tertiary? Well, no hydrogens on that carbon there that contains the bromine. So it is a tertiary. It's a tertiary alkyl halide. So what things favor tertiary alkyl halides? Sn1, E1, and E2. Well, good news, we pretty much eliminated Sn2. Okay, so now we know it's either going to go Sn1, E1, or E2 because of tertiary alkyl halide. Water. Well, what do we know about water? Well, it's a weak base. It's not a strong base. It's a weak nucleophile. So we go back to our chart here. Sn1 prefers weak nucleophiles. E1, and note Sn1 conditions and E1 conditions are identical. Therefore, we now know this is going to go Sn1 and E1. We're going to put an OH. We're going to turn this into an alcohol. Recall, for the Sn1 reaction, first step is leaving group leaves, makes a carbocation. For substitution, the weak nucleophile, the lone pair on this oxygen, will attack that carbocation. Our product will then have this carbon bonded to this oxygen. That oxygen will have a positive charge on it and two hydrogens on there, and every time our product of a substitution reaction has an oxygen or a nitrogen with positive charge and a hydrogen on it, deprotonation happens. More water will come in, take that second proton, and will make that alcohol. All right, so our Sn1 reaction, leaving group leaves, we substitute OH on there through water. E1, well, here's our alpha carbon. There's hydrogens on this beta. Hydrogens on this beta also, but they are the same. Just rotate the molecule 180 degrees, the product, you get the same thing. Here's alpha carbon. There are no hydrogens on this beta carbon here, so we don't have to worry about that. We just get this elimination product right here. It's a stray mark. Okay. Now, let's look at our next one. This one's a little interesting. We have a secondary alkyl halide. Alkoxide, a strong base, strong nucleophile. Well, if we look at our chart here, okay, secondary, none of these are secondary. So if none of them are secondary, note this means Sn1 is favored by tertiary. Secondary can do Sn1. Secondary can do Sn2. It prefers primary, but secondary can do Sn2. Secondary can go E1, secondary can go E2. So a secondary alkyl halide, a secondary substrate, doesn't tell us anything. All mechanisms are still in play. Strong base, alkoxide. We recall from our chart, strong base means either Sn2 if it can act as a strong nucleophile, or E2 if it can act as a strong base. Methoxide can be a strong base. It can be a strong nucleophile. That's all the information we have. Therefore, with a secondary alkyl halide here and a strong base, strong nucleophile, we will get both the Sn2 substitution product and the E2 elimination product. Sn2 Just going to substitute this OCH3 on for that Br, get the ether. Elimination, we just get that double bond. All right. Well, what else can we do here? All right. Let's look at this guy right here. Tertiary alkyl halide. Methanol, a weak base, weak nucleophile. Well, tertiary alkyl halides, weak base, weak nucleophile, means Sn1 and E1. So you can get the Sn1 product and the E1 product also. Okay. So, note with the substitution reaction or the elimination, the first step is leaving group leaves to make the carbocation. So we're going to end up with this tertiary carbocation. For the substitution reaction, lone pair on this oxygen will attack the carbocation. Yes, this will have a positive charge on that oxygen now, but it's got a proton on it. Deprotonation will occur. Positive charge, deprotonation, we put the OCH3 where the Br was. If we run the E1 mechanism, again, the first step is we generate the carbocation, tertiary carbocation, then the methanol, a weak base, will come in and take a beta hydrogen. Well, here's alpha, where's beta? Well, we have a beta methyl here. This is also a methyl. Since these are both methyls, it doesn't matter if it takes this one or this one. These hydrogens, you get the same product. But this is a CH2 here. So we've got the beta hydrogens on CH3. On the other side, beta hydrogens on CH2. We can get both products. We can get the carbon double bond to this carbon over here if the methanol takes a CH2 beta hydrogen. If it takes a CH3 beta hydrogen, we'll get the double bond at the end there. What does Zaitsev say about major product? Well, two hydrogens on the carbon of the double bond here. This is di-substituted, geminal di-substituted. This one's tri-substituted. Zaitsev says more substitution, more stable. This will be the major product. All right. One last thing to discuss when we're looking at substitution versus elimination. As we have mentioned before, note all our bonds here are sigma bonds. When we do a substitution reaction, all our bonds are sigma bonds. We start with sigma, we end with sigma bonds. When we do elimination, we start with sigma bonds, but we end with double bond. We make a double bond. Recall a double bond is a sigma bond plus a pi bond. Also remember that pi bonds are not as stable as sigma bonds. We generate a pi bond, we generate a less stable bond, which means elimination reactions are endothermic. To run this path here, you need to add energy because the product is most likely going to be less stable due to the pi bond than our reactant was, because reactant had all sigma bonds. So elimination reactions tend to be exothermic. Good news, we have our good old buddy Le Chatelier. Now what does Le Chatelier say to do if you want to favor an endothermic reaction? Yeah, that's right. Le Chatelier says if you heat up, if you add heat, increase the temperature of an endothermic reaction, you can push it towards the products. What this means is whether you're doing E1 or E2 reactions, heat favors elimination. Heat favors elimination. If you want to run this reaction and you're like, oh, I really want to focus on getting the E1 products. I don't care so much about the Sn1 products. I really want to focus on the E1 products. Heat it up. Add some heat and you will favor elimination. Can you get rid of substitution? Well, I don't know about that, but you can get more elimination products. What if you didn't want the elimination products? You wanted the Sn1 products. You wanted to favor substitution? What's opposite of heating it up? Yeah, cooling it down, running it in an ice bath, cool it down some. You will favor the substitution products in that case. All right, this ends the chapter. And good luck studying with this. I'll probably be posting some example problems being worked out soon.